This video will help us understand some of the vocabulary from Chapter 2. First, we'll look at equivalent expressions. Let's say that you have 4 quarters, as shown here, and I have 6 dimes, 1 quarter, and 3 nickels. If you total it all up, we both have $1, just in different ways. These two expressions of $1 are equivalent. 4 quarters is the same as, or the same amount of money as, 6 dimes, 3 nickels, and 1 quarter. These two expressions of $1 are said to be equivalent because they have the same value. Similarly, with algebraic expressions, we can have two expressions be equivalent. Now, I'm representing the expression on the left, 4 times x plus 5 plus 5, using these blocks. The blue bars represent the unknown x, and the yellow squares are 1s. So this 4 times x plus 5 is represented here as, well, here's x plus 5, x plus 1, 2, 3, 4, 5, and it's there 4 times. And then an additional 5 1s over here. On the right-hand side is an expression 4x plus 25. And you see 4x bars, and then this array of 25 1s. If you count the x bars on each side, you'll find that they're the same number. And if you count the small yellow squares on each side, you'll see that they're the same number. So the models are equivalent to one another because they have exactly the same value. And we say that these two expressions in this equation are equivalent. Now, here's an example of using some of the properties that we've learned to create equivalent expressions. This is a process that we know as simplifying. So if we start with 5 times x plus 3 minus x, we can create an equivalent expression by using the distributive property, changing this to 5 times x plus 15 minus x. We can interchange the 15 and the negative x, writing 5x minus x plus 15, and this is an equivalent expression to the one before because it has the same value. If we add like terms, 5x minus x, or combine like terms, we get 4x plus 15. That is equivalent to the original expression. So all of these simplifying steps have changed 5 times x plus 3 minus x into the equivalent expression 4x plus 15. If you remember the chart of basic moves, we used the distributive property to remove parentheses, but using the distributive property on an expression also makes an equivalent expression. And when we combine like terms, that is, collect number and variable terms, we also make an equivalent expression by doing that. Now, let's take a look at what equal means. When we say that two quantities are equal, we mean that they have the same numeric value. Now, in this equation here, 5x plus 3 might not look the same as 18, but our goal is to find a value of x that makes these two numeric values equal. Now, if we go back to our original picture, 4 quarters equals 6 dimes, a quarter, and 3 nickels. Those two quantities are equal. Now, because they are equal, we can add, let's say, 5 cents to each one of those quantities, and even though they're different, they stay equal. So here's 4 quarters and 5 cents, and here is 6 dimes, 1 quarter, and now 4 nickels. So we added 5 cents to each side, and you'll see that each side is now worth $1.05. They're still equal, even though we added something to each side. Similarly, if we start with the same configuration, $1 each, and we subtract 25 cents from each side, taking away 1 quarter, and here taking away 2 dimes and a nickel, you'll find that we have 75 cents on each side. They are still equal, even though they look different. We can also take this original equation and multiply each side by 2. If we multiply 4/4 by 2, we get 8/4, and if we multiply 6 times 1/4 and 3 nickels by 2, we get 12 dimes, 2/4, and 6 nickels. We have a total of $2 on each side. So again, when we multiplied both sides, two equal things, by the same thing, by 2, we have equality maintained. And similarly, if we divide each side by 4, in other words, if we take these 4/4, divide by 4, leaving only 1, and divide this by 4, leaving also 25 cents, we divided equal quantities by 4, by the same thing, and what's left is still equal. So those represent 4 properties of equality. And we can summarize it with this table. When we add or subtract equal amounts from both sides of an equation, we are using the addition property of equality and the subtraction property of equality. When we multiply both sides by equal amounts, we're using the multiplication property of equality. And when we divide both sides of an equation by equal amounts, we're using the division property of equality. And when we use any one of these basic moves, the two sides of the equation are still equal. And that brings us to equivalent equations. We say that two equations are equivalent if they have the same solution. And when we use the properties of equality on an equation, the equations are equivalent to each other. Now here's a sequence of things that we might do when we're solving the equation 5x plus 3 equals 9x minus 13. First thing that we might do is subtract 5x from each side. On the left side we have 3. On the right side we have 4x minus 13. This new equation is equivalent to the first one because it has the same solution. If we now add 13 to each side using the addition property of equality, we create a new equation, 16 equals 4x, which has the same solution as the previous equation and as the first one. And when we divide both sides of this equation by 4 to get 4 equals x, we have an equation that's equivalent to the first one. Of course, it's easier to tell the value of the unknown looking at the last equation, 4 equals x, than it is looking at the first equation. And that's the whole purpose of using these properties, is to take a rather complicated equation and change it into a very simple equation where we can see the answer. We can verify that these two equations have the same solution by substituting 4 for x in this equation. So 5 times 4 is 20, plus 3 is 23. 9 times 4 is 36, minus 13 is also 23. So this first equation has a solution of 4. This last equation has a solution of 4, so those two equations are equivalent.